speaking on coherent constructible correspondence and homological correspondence.
And part 1. Yeah. So thank you very much for the invitation, and I'm somehow sorry if you hear this talk again and again. Okay, so this is joint works. This talk is based on joint works with Melissa Liu, who is sitting there, and David Truman, who is also sitting there, and Eric Zaslow, well, who is not there. Okay, first, let's. This talk will be, as the title suggests, I will talk about 2 parts. The first is coherent constructible correspondence. The second is its implication on homological mirror symmetry. So first, I will fix some notation for torque variety. And for torque variety, it's always given by a fan. Sigma is a big fan. So this big sigma lies in NR. N is a lattice, so the standard notation, and NR is is an n-dimensional vector space, and this M is a dual of N, and sigma is given by a set of cones. So it's sigma R. So it's sigma 1, sigma 2. So sigma I lies inside NR. Okay, so this is the notation. So for example, if sigma equals to, if we have a fan like this, this will give 0p2. This is a very standard story. And I always assume our torque variety is complete and smooth projective. Although the first part of the story does not require this condition, but since I'm talking about homological mirror symmetry, especially T-duality, so basically I will require the smoothness, because otherwise there's no easy differential geometry on this torque variety. Okay, so here's the second. After we fix this torque variety notation, this is a coherent constructible correspondence. So first is some motivation for that. R is the number of 1 cones. So this torque variety, x sigma, so here this x sigma equals P2. This x sigma is defined as a quotient. So here, say R minus a closed part, which is prescribed by the fan, and quotient by a torus, complex torus. And this di is a divisor simply given by, is simply the ith plane in this, say, R. And this di, little d, this di without tilde is image inside this T invariant divisor. Okay. So there's a Morelli's theorem. So there's a motivation for this coherent constructible correspondence. There's a Morelli's theorem saying that if, well, just part of, because I'm just stating a weak version of that. So the T equivalent K group of this X sigma is embedded into, there's a map of, injective map of this group into this this piecewise constant function on MR here. If I forget to define this, what MR is simply the n-dimensional real vector space dual to NR. So
sorry, in classical, for symplectic people terms, the
moment plane.
The one cone is dual to the faces of the polytope.
Yeah.
That's not polytope.
Yeah, one cone, yeah.
The one cone is dual to the, and MR is the polytope itself, or?
MR is the plane that the polytope sits in, the moment plane.
Is the plane that the polytope.
Yeah.
When you say piecewise, does it have to be some
piecewise constant function?
the pieces have to be.
For example, like the polytope.
The pieces of the polytope, or it can have nothing to do with the polytope.
It basically has the shape of polytope. So, for example, if you have this, if this vector bundle is ample, if this is ample, so the K group class of this vector bundle gets sent into a, so this integration function on this polytope, which is a moment polytope of this line bundle. You can think this where there's a combinatoric definition. That's this x by I is greater or equal than minus ci x lies in MR. Is that
so piecewise constant function is just a number on each face of the polytope?
No, just for example, in this case, if this is ample, this delta c is a polytope. This is simply 1 on this polytope and 0 otherwise.
So it's 1 on all the faces?
Yes, including 1 on the face and 1 on the interior. Right.
Could you give the example of P2?
Yeah, for example. Sorry. So for P2, so here's V. So I label this one cones by V1, V2, and V3. So O, D3, this D3 corresponds to this one cone. That sends into 1 on this polytope 0, 0, 1, 0, 0, 1, and 0 outside. Of course. Right. So this is a function on. So this is a function on MR. It is 1 on this polytope and 0 outside. So this is O3, OD3. This OD3 gets sent into. Yeah.
You can draw an example of the direct sum of two line bundles.
Direct sum of two line bundles. So.
I mean, are there piecewise constant functions that are not constant on the whole polytope? It's the definition we don't get.
Yeah. I mean, first, this is injection. This is injective. So it doesn't. It's not a. I'm stating a weak version of that. So it's not. I'm not saying these two are isomorphic. Yeah.
Is there some sort of nice characterization of the range? I mean, you're telling me that there's.
I will tell you the next characterization of the range in the categorical sense, since this coherent-constructible correspondence is a categorification of this theorem. I will tell you the characterization in the categorical sense of the range in the categorical sense. Oh. Okay. So here, the so-called categorification.
Sorry, can you just one more example? If you take O of m times D3 here, instead of D3, you just have a multiple of D3. How does the right hand side
So n times D3, right? Is it this example?
Yeah.
Yeah. So it goes to this one. 0, 0. So here this becomes minus, here is n, so this is minus n. So here's n0.
So it's 0, it's n times.
Yeah. Here's 1. This is larger triangle. And for example, if you want OD, here another example is OD1 gets maps into here's 0, 0, minus 1, minus 1, 1, and minus 1, 0. Here is 1 and 0 outside. So you think about there are three lines perpendicular to each of these one cone, and you move this line, which is perpendicular to V1, backwards one step, and this prescribes this polytope here. So here's the origin. Categorification. So there's a categorification of this theorem, saying that we can think about the derived category of coherent shifts as a kind of categorification of the K group. So this derived so here is a DG category of coherent shifts on X sigma. So since there's T equivalent K group here is T equivalent coherent shifts. Well, here and for now it's a quasi-embedding, so it is a DG functor and full and faithful in the homotopy category to this category of constructible shifts on MR. So if you So the coherent shift T is a DG category of coherent shifts. A DG, you can complex of quasi-coherent shifts with coherent homology. Coefficients are complex numbers. Yeah. Although we have here we don't require the coefficients of variety to be defined on complex numbers, but since I'm talking about homological mirror symmetry later, so I require. Yeah, but if you set let the base field be K here, this coherent shift will be K module. Yeah, but for here let's set the base field. Let's set the base field to be C, since later we'll be dealing with homological mirror symmetry. So DG category of coherent shifts here, and so this DG category of constructible shifts. So it's field, base field. So over, so let's set this. Okay. I will very briefly talk about the proof. Well, becomes full and
In the derived category?
yeah, full and faithful function in the derived category, and it itself is a DG function.
Faithful or fully?
Fully faithful. Yeah. Okay, the proof, or basically a sketch of proof, is basically first as I embed this category of coherent shifts into the category of quasi-coherent shifts, because, and consider this shift. This I call it theta prime.
When you say coherent, it's the Derived category of coherent.
This one?
Yes.
DG category. Yeah. So for any, this is any cone in the fan, and this chi is a character, which character in M. So J sigma is for any cone. We have a affine variety associated with this cone, and this embeds into this, the original toric variety. So this is J sigma, equals J sigma prime. Of course, we have this theta prime here. So J sigma prime, the push forward of the structure sheaf on this x little x sigma, the x little sigma, but with some equivalent structure chi.
I didn't understand what chi was.
Okay, it's this chi is inside a character inside this inside M. Chi is character inside M. Is that okay? And so this is basically the structure sheaf on this x little sigma and push forward, but the structure sheaf twisted by an equivalent structure prescribed by chi. And have defined another so-called theta sheaf. So this has to be a constructible sheaf, equals J sigma, and a push forward with proper support, proper push forward. So I will talk about this. I will say something about this. The shape of this. This is simply a polyhedron shaped area inside this XMR. So I will, for example, this is P2. This is P2. This is sigma. Here, the sigma check equals to something like that. So it's dual, which lies inside MR. This part, the dual to this fan, and shift by this. So you move, since this is 0, if you don't shift it by chi, but you shift it by chi, so this becomes chi. So this point. So this is, well, here is, you can think it's a constant shift here, and I shift by degree n. So this is, I don't want this. Okay, so I define these two building blocks of shifts, and we can compute the Helm between these shifts. So their Helm relation is very sigma prime is very simple. Oh, yeah. So J sigma, of course, is this shape embeds into MR. Equals to C, a piece of C at degree 0, when this sigma check chi 1, 2 check plus chi 2. And 0 otherwise. So by this calculation, so their home relations are essentially the same. We can conclude that the DG category generated by theta on this constructible shift side and the DG category generated by the theta prime on the quasi-coherent shift side, they are equivalent, or they are quasi-equivalent. So that's the first part. First part of this proof. The second part of the proof is, well, we have to show that this category of coherent shifts lies inside this DG category generated by this quasi-coherent shifts, theta prime, which is, since this one is generated by vector bundles, so we can resolve any vector bundles simply on this by this checked resolution. So J. So let's say I equals to X. So here is X sigma I, and say Ij equals to X sigma I, X sigma J, and sigma 1, sigma here, V are top dimensional cones. So using just check resolution, I can write down any vector bundles in terms of this, in this check resolution, and each vector bundle restricted to this affine variety is essentially has to be the structure shift twisted by a character. Okay, so this is basically a sketch of this proof.
Can you recover the non-equivariant case by modding out the translations?
Yes, but this doesn't work. Well, this has some subtleties if we, well, here, yes. And later, if we want to characterize the image, the range of this embedding, this characterization has some subtleties if you quotient by the, if you pass to the non-equivalent case. But this embedding, if you simply think it as a quasi-embedding functor, it's okay. Okay, here's an example that home of O1, O2, well, we know there are this is a three-dimensional space on P2. And here's O2. Well, if we don't worry, so here's non-equivalent. This is a non-equivalent home. So we don't worry about its position. So we can see if we put this at different equivalent structure, essentially you can put this little triangle into this larger triangle in three ways. So this corresponds to the three-dimensional home of this O1 to O2. So here's the constructible sheet. Yeah, the composing of three equivalent pieces. Yeah. So here's the so this shifts. Since this, the proper push forward of constant shifts on this smaller region, there's a morphism from this smaller region to this proper push forward of constant shifts on this larger region. So essentially, if you count, there are three possible push forwards. Okay.
That picture on the right, is the triangle in the middle unshaded? Is that what you're thinking?
Unshaded is something that cannot be mapped into. I mean, this larger one, this larger triangle corresponds to the constructible shift corresponding to O2.
On the whole thing.
On the whole thing,
Right.
yeah. This, yeah. Okay, so here's a characterization. of images. So of the range. So here's the theorem. So still is well, this is simply an enhancement of that this functor actually from the category of coherent shifts to this category of constructible shifts. If we specify the microlocal behavior, we can construct a conical Lagrangian directly from the torque data, and require our shifts to have this microlocal support, which is their microlocal support to be subset of this conical Lagrangian we construct, and we require the shifts to be compact supported on MR. So if we restrict to these shifts inside this category of constructible shifts on MR, so this is equivalent to this one. This is a quasi equivalence. Lambda, I will define it immediately. Yeah. So it's first for now, we can construct this lambda sigma, this conical Lagrangian, directly from the torque data. So it's a conical Lagrangian inside theta inside T star MR, and this one is shifts. Of course, constructible shifts. First we have compact supportness, so we have another small letter c for compact. So this theta shift itself doesn't work. Is not in that category because it's not compact supported. So of course, it corresponds to quasi-coherent shift, not coherent shift, as you can see. And the second is their microlocal support have to be a subset of this lambda sigma that we will construct. I will construct it here. So this lambda sigma is simply sigma inside. So for any fan inside this, so for any cone inside this fan, and for any tau inside this character lattice is tau plus sigma. So this lies inside MR, and this lies inside NR. So this is, if this is k-dimensional, this sigma perpendicular is n minus k-dimensional. So if we multiply them together, we have an n-dimensional conical Lagrangian. Here's an example that if I look at P1 with sigma minus, sigma plus, here is sigma 0. So this origin point, we have three cones in this fan, and then we construct them. I will draw the lambda sigma. This lambda sigma, first is sigma 0 perp. Well, since sigma 0 is simply the origin, so it is simply, so its perp is a whole piece of MR. In this case, it's just one-dimensional. It's a line. And you shift it by all possible tau, but you still get a line. And sigma plus perp, sigma plus is this positive ray. Its perp itself is 0. And so sigma plus perp plus tau is a bunch of points, integer points, which lies inside MR. And this minus sigma plus tau for all tau, minus times sigma plus per plus tau equals to, in this case, here. So we have a bunch of half ray. So this is NR direction. Horizontal is the MR direction. And the other part, which is similar, so I say it here. So the other part which is similar, I'll draw it here, sorry. So it is minus sigma minus cos sigma minus tau plus so it's minus sigma minus perp tau equals to still this. Okay, so we have to take the union of all these conical Lagrangians. What we have is, first we have the base of MR and all this fiber over integer points. So this is a subset inside NR times MR. Tau lies inside M, so for all characters.
So M that's the integral tau.
Yeah. So here, so you have different tau. So I have this. So have this minus ray starting from integer points in M, different integer, all integer points. So summing them together, we have this conical Lagrangian. So here's an example. So let's look at the singular support of the proper push forward of C at 0, 1, shifted by 1. And by that, and this this constructible shift corresponds to O d minus. Minus is that one cone there, and this one equals to here is minus 1, here's minus 1 0. Sorry, here's 0 0. Here's 1 0, and we see its microlocal support lies inside that big skeleton. Yeah, this. Okay. Shift by one is for some duality reasons, because I want, so one of them is the direct push for the direct image of this direct image of on 0, 1, which corresponds to anti-ample bundles, and if we have to take vertical dualities, therefore have to take a shift by 1.
Okay. This should not change the singular support.
Change the what? Change.
Singular support.
Yes, yes, it will change the singular support. Yeah, yes, this one, say minus 1 0 actually, and this corresponds to, for example, 0 1 is this one. Sorry, singular support, but this singular support still lies in this big skeleton.
Yes, but the shift by 1, that has no influence of the singular.
No, it doesn't. No. But if you compute the, in order to make this correspondence correct, if you compute their home, then you have to make the shift to make the degree correct. Okay. Now let's shift gear and let's talk about this the application of this correspondence into homological mirror symmetry. So homological mirror symmetry for torque varieties, of course, is a very long story, and And a lot of people have made a great contributions in this, and many of them are sitting here. But for here, for the part of this talk, I will simply talk about this X sigma, which this B model here, which means complex geometry here corresponds to symplectic geometry inside this Lambda-Ginsburg mirror. And I will be very careful here because actually we don't use this superpotential. So we simply end up with Lagrangians inside C star n. But for now, I don't know its relation. This our version of homological mirror symmetry, we don't know its the relation of our Lagrangians with respect to this superpotential. Well, I don't know it very clearly at least. So here, with just one side, HMS is a B model. Here's complex geometry on X sigma. So here's coherent sheaf of X sigma should be equivalent to the original conjecture should be equivalent to the Fukaya-Saito category of C star n with respect to this superpotential. And our theorem there already builds the equivalence of category of coherent sheaves to constructible sheaves on MR. And we know there's a lot of story between constructible sheaves and Fukaya categories. And here I will invoke the version of unwrapped Fukaya category. I will say something about it, but for now, let's simply think it as a category, Fukaya category defined on T star MR. So what we have is, so they have a so simply applied to our case, so let's state their theorem. So for any y is analytic real analytic manifold, they have equivalence of constructible sheaves on Y, and with their version of unwrapped Fukaya category on T star Y. Unwrapped Fukaya category. Well, this is an infinity functor. Left side is a DG category. The right side is an infinity category. So we can apply this theorem to our theorem. I don't know where is our theorem. So this coherent sheaves X sigma. So we have built a quasi-equivalence of this constructible sheaves. And their functor tells us this category is embedded into the category of into the Fukaya category of T star MR. And if we restrict ourselves to lambda sigma here, so we restrict our macrolocal support to be lambda sigma. So this one version of their theorem says that actually the image should be Lagrangians whose infinite part is prescribed by whose infinite behavior is prescribed by this lambda sigma. So this is also a equivalence. So this is mu. So combining these two functor, we have a category of coherent sheaves of X sigma to the Fukaya category of T star MR lambda sigma.
So the Lagrangian in this Fukaya category are Lagrangian which at most go to infinity along lambda sigma sometimes.
Yeah,
But it could do less.
you could, of course, it can be the base manifold. So I will say, what I will say is that this is a version of homological mirror symmetry because the right side does not, at first glance, does not look quite like the Foucault-Seidel category on the say star n. But if we forget, as Chris once commented, if we forget the equivalent structure, actually we have, although there is some technical issue of this category of constructible shift, at least we still have this embedding, quasi-embedding to the Foucault category. And here, so if we forget this T action, here we wrap around this MR by the lattice action of M. So T star over real torus, actually. This is at least, as far as we know, it is a quasi-embedding. Okay, and T star of the real torus, symplectically, it is C star n.
Sorry, it's MR divided by what?
M. M is the lattice. Yeah, it's real plane divided by the, yeah, so you have a real torus, T star of a real torus. So it is symplectically. So this is one reason I call it homological mirror symmetry. Although the Lagrangians we get in this case does not quite, well, we don't know whether they should be, whether they are the vanishing symbols of this superpotential or not. Yeah, so it's somehow near this this original conjecture. And I think the most important reason that we call this homological mirror symmetry because this functor, kappa mu times kappa, agrees with T duality. So here's the Foucault category in the sense of nether. That's all. Is that the object is exact Lagrangian on T star y and possibly non-compact. Of course, reasonably behavior at infinity. What I want to say is it's unwrapped because the morphism is L1 and phi t L2. This is the home of L1 to L2 in this case. And this little phi t is a normalized geodesic flow outside the compact part. So this normalized geodesic flow is simply the Hamiltonian flow of the length of the fiber.
This is the unwrapped version. So
Unwrapped version.
So T is very small.
T is very small. Okay. So the theorem of Nader-Zaslow here, so here's Nader-Zaslow, and they proved for the embedding, and Nader proved for the equivalence. That is, this one is a equivalence, especially so a sheaf, I call it standard sheaf, is I star Cu. U is a subset of Y, corresponds to the so-called standard Lagrangian. Here, at first I write down its form. It's gamma df restricted on U plus Tu star x. This U is a locally closed manifold, submanifold. So if U is simply an open subset, in this case, if U is simply an open subset, for example, open subset on a real line, this is U. So this is a standard Lagrangian. It should look like this. This is T star R. And there's a dual version of this statement saying that the costandard, that is the vertical dual of this I star Cu, corresponds to this costandard Lagrangian. In the one-dimensional case, so this is U. The boundary of U are these 2 points. It's simply this. Okay. Okay, now is T-duality. So the T-duality is, of course, is once proposed by Strominger and Zaslow is, but I will simply talk about this very specialized version of that we use. First, I delete all a anti-canonic divisor. So this is the direct sum. So the union of D1 to dr is an anti-canonic divisor. This is simply x correspond to the 0. The 0 point as a cone, that is say star, to the n. Maybe, sorry, maybe I'll write it here because this is somehow. So here, this is x sigma minus 0. That is say star to the n. And this is nr over n times nr gets mapped to nr. You can simply think this coordinate by coordinate is zi equals to e to yi plus I theta I. And this maps to log, so maps to y1, yn. So these are coordinates of the say star n. On its dual picture, the base is still nr, but a fiber is a dual of nr quotient by n. It's mr quotient by quotient by m times nr, this one. And the coordinates equal gamma I, the second one still denoted by yi. So there's a universal cover of this story. So the universal cover is mr times nr. This universal cover is simply nr times nr. So for any line bundle, so it's still T equivalent given in this form. We can find a first we associate a meromorphic section at SI so this is a meromorphic section. SI is DI. SI itself is a holomorphic section, so the SI is simply prescribed by this divisor DI. So define a function that is log S, so I call this S, depends on C. Of course, we have a linear metric. This H is TR invariant metric. So it is invariant with respect to the real part of this torus action. So from this data, we can construct a Lagrangian CH, so which depends on C. C is simply the data that describes this line bundle, and H is a metric on this line bundle. This is a metric, which from NR to MR, simply by gamma j equals to 2 pi over 2 yj. So since this is TR invariant, so on this picture, it simply does not depend on theta I, simply depends on the real part is yi. So we have this is a graph. So this is a graph of the following map. So here I have some remark. The first part of this remark is this psi CH is a moment map of the curvature form of this line bundle with respect to this metric, and is quasi-isomorphic in the Fukaya category if you choose different metric, different TR invariant metric. And so if this is ample, or anti-ample, so negative is ample, then this Lagrangian, I call it Lagrangian itself, I call it L, CH, which depends on C and H, although its quasi-isomorphic class in the Fukaya category does not depend on H, it only depends on C. Then this L, C, H is a graph. First is a graph from NR to MR, but you can invert it in this case because its range is simply the polytope delta C or delta minus C for this anti, or for delta C. Yeah. So the theorem, what we prove is that if Ci di, if this is ample, then so it's F if this is ample, then this Lagrangian is inside the Fourier category and is quasi-isomorphic to the standard Lagrangian over this moment polytope. So this so this is equal to, so this is a T-dual Lagrangian, and this one is kappa times, this is a composition of our coherent constructible correspondence, and this microlocal functor given by Nader and Zaslow, that is so I don't have any time. So let me stop here. Sorry.